happen is that pure silicon will form around that silicon seed crystal. Then they actually just pull out the pure silicon, leaving where you get this pure silicon rod, and then leaving behind in the solution all the impurities. Okay, so that's a way to, and that's actually similar to how freezing is used to purify water. Okay. The freezing method is based on the fact when an aqueous solution freezes, the solid that separates from the solution is almost pure water. Reverse osmosis uses water movement from a more concentrated solution to a less concentrated one through a semi-permeable membrane. So let's take a look at figure 13.8 on page 452. And that shows it shows this. Okay, so let's see. It shows this container here. We have this in the semi-permeable membrane. And you got a solution on one side and a solution on the other side. And what they also show, we'll seal this here. And they show like, well, we'll do this. Okay, so here's there's water on one side. So if we wanted to purify water, first the semi-permeable membrane has to be permeable to what substance? Water. Okay, so this allows water to pass through only. Okay, so water only is going to pass through the semi-permeable membrane. Let's say you have some seawater, and we put seawater on this side of the semi-permeable membrane. We want pure water. So what do we put on the other side? Pure water. Pure? Yeah, pure water. In normal osmosis, in which direction will the water pass through the semi-permeable membrane? So it's going to go, in normal osmosis, it's going to go from the water to the seawater, or the seawater to the water? This is going to go from right to left or left to right? Right to left. Okay, so it should go, in normal osmosis, it should go this way. Okay. Now, osmotic pressure is the pressure required to stop normal osmosis from occurring. Okay, so as this happens, we would see this water level rise. Okay, so then the two levels are not going to be equal. Okay, so osmotic pressure is the pressure required to stop normal osmosis from occurring. So when you're designing a reverse osmosis system, you've got to calculate that pressure so that instead of water going from right to left, it's going to go from left to right. Okay, so this is normal. This is for normal osmosis. And this is for reverse osmosis. So let's calculate the pressure, this osmotic pressure, so that we can get a reverse osmosis system to work. So according to problem, let's see here. This is actually problem 13.101 on page 464. And it says, let's do part C. What is the minimum pressure in atmospheres that must be applied to seawater at 25 degrees for reverse osmosis to occur? Okay, so they're saying that you want to figure out a minimum pressure the temperature is 25 degrees and the concentration of salt in the water is 0.70 molar. So based on this information, can we calculate the minimum pressure? And what equation will we use to calculate? Yeah, so what I'd like you to do is calculate that minimum pressure using this osmotic pressure equation. Okay, so let me erase this stuff here. Okay, so in this diagram, what we need to do is we need to apply a pressure. So we need to apply pressure to this side of our reverse osmosis cell to stop normal osmosis from occurring, and then to get the reverse osmosis process going. That's a good question. So for salt water here, we want to use I equals 2Q. Okay, so let's plug in our numbers. 34.2. Okay, so for salt water, for NaCl, I equals 2. So let's see, plug in our numbers. We have 2 times 0.70 molar, or moles per liter. Then for the temperature, plug in the temperature in degrees Kelvin, that's 298. Okay, so let's see, that cancels out. And those cancels out. These cancel out. So we'll be left with units of atmospheres. So then we plug all these numbers in, and we have 34.2. So this is the minimum pressure required to stop osmosis from occurring. Is this a high pressure or a low pressure? This is high pressure. So how would that pressure be applied to the reverse osmosis cell? What would you need? Yeah, a compressor or a pump. This would be a pump or a compressor. To get those pressures. So that's very high pressure. One thing is that depending on what else in the seawater, these membranes get clogged. So they need to be cleaned periodically. So note that quite a bit of energy is required for these pumps to achieve 34.2 atmospheres just to get the reverse osmosis, because that costs money. And then the other thing too is these membranes get clogged, so they need to be maintained, either cleaned or replaced periodically.
Do they put those on ships out at sea just to get the pressure?
Yeah. The other thing too, because you can buy these reverse osmosis systems for your house. If you want to, for example, you have hard water, and salinous water is pretty hard. So to remove the calcium, magnesium, a carbon filter won't remove the calcium, magnesium to soften the water. You actually have to use either a reverse osmosis system, or you could use a ion exchange column, which is either potassium chloride or sodium chloride. One problem with using salt in an ion exchange column is that if you or someone in your family has high blood pressure, you don't want to be taking in more sodium. So anyway, these are some disadvantages of reverse osmosis. But anyway, it's actually pretty expensive because you got to run these pumps. And then the maintenance too for these filters. can be expensive. So generally speaking, this is probably the cheapest way to purify water. Distillation, is this cheap or expensive? That's expensive. It's expensive because you gotta use heat to boil the water. Although we think of water, we have water and we use water all the time. Water actually has a pretty high boiling point. It requires quite a bit of energy to boil the water. So that's why distillation is rarely ever used to purify large amounts of water. It's too expensive. So this is the typical way, filtering, ozone, iodine, or bleach. Okay, and then if you want, you can take a look at these websites on reverse osmosis. Oh, so let's talk a little more about coffee, since we're almost finished with that lab. So coffee has over 1,500 substances in it. I think I told someone asked me that question in lab, and I said, 100, 200. Well, a lot more than 100, 200. Of those 1,500 substances, 850 are volatile substances. So these volatile substances mean that they have a high or low vapor pressure. Actually, high vapor pressure. Yeah. So these are the substances which, at least some of these substances, which are volatile, give the smell or the aroma of coffee. And then you have 700 soluble substances, and this means soluble in water. And I looked up a few of the substances. So here's 2-furfuryl-thiol gives coffee its roasty or coffee smell. Based on the name, what functional group is in this organic compound? Yeah, so the OL means it's an alcohol. Actually, a thiol is a special case. So the OL means it's an alcohol, which is the OH group. If you have a thiol, this is actually the SH group. So you substitute a sulfur for the oxygen, for the thiol. Many thiols